You've followed all the steps in the troubleshooting flow chart that you dug up out of your favorite service information system. You got into the last line and it says, replace the ECM. Does that make you nervous? Well, it should. What if you're wrong? What happens if you replace the ECM and it doesn't solve the problem? Or you replace the ECM and it immediately fails when you turn the key on because there's something you missed during your initial checks. If that situation describes you, then you need to watch what I'm about to show you. Hi, I'm Pete Meyer. Welcome to CARDONE PROTECH. This episode of CARDONE PROTECH is done in partnership with Motor Age magazine, the nation's oldest automotive trade publication. Check them out at www.motorage.com. The ECM, or any control module on the vehicle for that matter, are the most expensive fuses on the car. If you don't follow the tests that I'm about to show you, you could end up replacing a module that didn't need to be replaced. Or worse yet, replace a module and have it fry as soon as you try to start the vehicle. Focusing on the ECM, it's important to understand that it serves more than one purpose. It controls a number of devices on the engine, and in this regard, it's the switch that completes the circuit. But it's also a load, meaning that it requires the proper current flow in order to operate properly. That means there's got to be a good clean path from power and a good clean path back to ground. Any extra resistance on either side of these circuits could cause the ECM to make wrong decisions or no decision at all when it carries out its programming. The only correct way to verify the integrity of the power and ground circuits to the ECM is to test them using the voltage drop testing method that I shared with you in our last episode. And if you'll recall from that lesson, I told you that one of the things you need to do is connect to the circuit as close to the load as possible. In the case of the ECM, that would be back probing the connector. Of course, we need to know which wire to back probe, and I'll talk more about that in a moment. But I don't want to take any chance that I accidentally cross over and create a short circuit or other issue that could lead to damage to the ECM if it indeed proves to be okay. So I'm going to use an alternate method by using an alternate load. In this case, nothing more than a headlight. A load's a load and voltage drop is voltage drop. So I can use either method to accurately test the integrity of the power and ground circuits. Oh, by the way, there's always more than one on a control module. The first step is to use a wiring schematic and identify what pins on the module are supplying power and which ones are connected to ground. The next step is to use that same diagram to identify the connector pins that we'll need to access. With that information in hand, look up the connector pinout diagrams and identify where those pins are located on the connectors themselves. Be sure to look up the procedure for disconnecting and reconnecting the ECM. In some cases, you may have to perform a relearn or two, and you want to make sure that you're prepared to do so if that's the case. With the connectors removed from the module, we can begin our testing. An initial step is to take the time to perform a good visual inspection of the connectors themselves. Inspect the pins for damage, corrosion, or the evidence of fretting. Fretting is gradual wear in the connector surfaces caused by rubbing between the two, and it can be a source of voltage drop that can impact the operation of the ECM. You can use a pocket microscope, a good magnifying glass, or better yet, use your cell phone to take a picture of the connector and then blow it up so you can see it even better. Now, it really doesn't matter which side you start checking first, power or ground. I personally like to start on the power side. Specifically, I look for the wire that's hot at all times, the wire that supplies the power to the keep alive memory of the module. Typically it'll be labeled on the schematic as simply B+, or in the case of this model, VBAT for battery. I've identified it as pin number 40 on the third connector back, and it's a dark green wire. I'll put one lead on the B+ pin I identified, and I'll connect one side of my headlight to that. I'll connect the other side of the headlight directly to the battery negative post. If we've done everything right to this point, the headlight should be on and bright. Now I admit I'm going to cheat just a little bit. I have a specialty connector that allows me to connect my voltmeter and my test bulb to one single back probe. This way, when I make the connection for my test bulb, I'll also get my voltage drop reading, and I'll get it at a point that eliminates any concern for any voltage drop that might exist in the wiring for the headlight. I'll set my meter to measure millivolts. Most meters will only measure up to about 500 millivolts before they'll read OL, or over limit. If I see OL on my meter screen when I make my test, I'll know there's a problem. But before we take our first measurement, there is something I think that you should know about. It's something called ghost voltage. When you hold a lead in each hand, you may see the reading on your meter bounce around and not stabilize. This is ghost voltage, and it lets you know that your leads are not making good contact. Touch the leads together and the bounce should disappear, replaced by a perfect zero reading. Now I know the leads are properly connected, and any reading I get that remains stable can be counted on as a good reading. Back to the test. Place the negative meter lead at the positive battery post, and using a back probe, carefully insert the probe from the back side of the connector until it makes contact with the pin. Be sure to insert the probe between the wire and the weather pack so that you don't puncture the weather seal with the probe. And don't go any further than necessary to make contact. This eliminates any source of voltage drop in your extension leads and headlight connection from the measurement. Repeat this test for every power side circuit you've identified connecting to the ECM. Make special note of when that power is being applied. Is it hot at all times, or is it only on when the key is on? You must make sure that you test under those conditions. Finally, if you see any discrepancies in your testing, follow up on them and correct them before you move on. Once you've verified the integrity of the power side circuits, then we can move on to the ground side. Like we did with the positive side, we'll connect one side of the headlight directly to the battery, only this time on the positive post. Then connect the other side of the headlight to your first ground pin. And using the back probe technique that we learned earlier, test each ground until you've verified them all. And what if you do get an OL reading on the meter during one of your tests? How do you find the cause? Just like we learned in our last episode, work your way back to the battery using easy to access test points at first until the reading returns to normal. When that occurs, I know I've passed the problem and I need to head back the other way in smaller sections until the reading becomes bad again. The extra resistance that we're looking for lies between these two test points, and it's just a matter of continuing to narrow down the possibilities until the cause is isolated. Once you've verified the integrity of all the power and ground circuits attached to the ECM, the next item on the list is to check all the actuators that are attached and controlled by the ECM. A short in any of these circuits could be the reason that the ECM died. When an actuator shorts internally, its resistance goes down. And you may recall from a prior episode where we discussed Ohm's law and the relationship between voltage, resistance, and current, that when resistance goes down, current goes up to the point where the drivers in the ECM can't handle the load and they burn out. You'll need to check the static resistance of each actuator controlled by the ECM using your ohm meter. This also requires a bit more homework. let's see what information you'll need to proceed with your testing. Like we did before, we can use the schematic to identify the connectors and connector pins we need to test. You'll also need to look up the resistance specifications for the various actuators. Take the time to make yourself a checklist and work your way through it one component at a time until you've checked them all. But be careful. Just because you found one shorted actuator, it doesn't mean it's the only one. Be sure that you check all of the actuator circuits the ECM is in charge of. Early on in your diagnostic process, you should have verified that all the inputs going to the ECM are accurate. After all, the ECM can't work properly if it's getting incorrect information. You may also need to check the output circuits using the bidirectional commands on your scan tool. If you can turn the actuator on and off, then that means the ECM has that capability. If you find one that you can't operate, then that's where you might want to start checking your actuator circuits. In either case, make sure that you follow the tests that we've shown you today. You may find that the problem was simply a bad ground, and correcting that is all that was needed to correct your customer's concern. Replacing an ECM in that regard would have been a costly and unnecessary repair. If, however, the ECM is indeed bad, it's critical to find out why it went bad in the first place. Otherwise, you're just going to let the smoke out of that brand new ECM right after you install it. I hope that you found today's video helpful. And if you did, make sure you hit that subscribe button and don't forget the notification bell so that you'll be advised when the next CARDONE PROTECH video is available for your viewing. And as always, thanks so much for watching.